Atomic structure and symbolism. And now that we have a sense of the subatomic particles, that is, say atoms are made out of protons, neutrons, and electrons, how can we talk about them? How do we symbolize them? What are their properties? That kind of an idea. Here's a chart from the table from the book, table 2.2. Listing those three subatomic particles, electrons, protons, and neutrons, right? And just a little bit about them. So for example, both the proton and the neutron we find are in the nucleus. Remember those very small little pinpoints of matter right in the middle of each atom. Whereas the electrons are found outside of the nucleus, whizzing around in that space, which is mostly a vacuum. But every once in a while you might encounter an electron whizzing around out there. The charge, neutrons don't have a charge. They're electrically neutral, where the protons and the electrons have exactly the same charge, just opposite. One's positive, one's negative. And again, Millikan showed that it was 1.602 times 10 to the minus 19 coulombs. Well, because they're exactly the same charge, just one's positive and one's negative, we define what's called just the unit charge. The unit charge of an atom is the charge of one proton, or the charge of one electron. We're just going to call it, instead of 1.602 times 10 to the minus 19, we'll just call it plus 1 or minus 1. All right. Or technically, when we write charges out, we're saying there's one charge that's 1 plus or 1 minus. When we write charges, the plus and the minus actually follows the number. Okay. That's just a different unit. It's just a unit charge of an atom. It's just like saying instead of millimeters, we're going to use meters or something. Just a different unit, which is a little more convenient and easy to talk about when we're talking about molecules and atoms. Right. The fundamental charge, sometimes it's called, but unit charge, that's fine too. The mass. How much does each one of these little subatomic particles weigh? We're going to have to talk about exactly this. AMU is the unit that we're using here. It's called the atomic mass unit. Right. But right now, just look at these numbers. You can see the proton and the neutron, they weigh about the same. So they have the same charge. The electron and the proton have the same charge, but the proton and the neutron, all crammed in that nucleus, they have about the same mass, each one of them. Right? 1.007, 1.008, very, very close. They're about the same. Whereas look at this electron, 0.0005 compared to them. If you take that ratio, it's about 2,000. About 2,000 times more protons and neutrons weigh compared to an electron. So electrons don't weigh very much. Pretty small. Here's the mass, actually, if you convert the AMUs to grams. Here's the actual mass in grams of those. Alright, so here's the picture now we have of an atom here, figure 211. Big area, mostly a vacuum. Right in the middle is our nucleus, which has both protons, positive charge, and neutrons, no charge at all. What is the size of these things? What is the diameter? A typical diameter of an atom here they're showing as 10 to the minus 10 meters. That's pretty small. Remember, a millimeter, about the width of a coin, a little dime, if you will. Millimeter, that's about the length of that. That's 1/1000th of a meter, right? You break one of those down into 1,000 pieces, you get a micrometer. Break 1 micrometer into 1,000 pieces, a nanometer. Now we're down to 10 to the minus 9. You got to break that down to 10 pieces, and finally you get 10 to the minus 10. So this is unimaginably small. But it is the unit, or it is the size, I should say, that's representative of an atom, about the size of it. And so we define a new unit called an angstrom, symbolized by an A, a little circle on the top, an angstrom, as exactly 10 to the minus 10 meters. Because that'd be a perfect meter when we're talking about measuring atoms and such. Alright, so the diameter of a typical atom is 1 angstrom, 10 to the minus 10. What about that nucleus, that little teeny pinpoint of matter in the middle? 10 to the minus 15. So that's 10 to the 5th. 10 times 10 times 10 times 10 times 10, 10, right? That's 100,000. 100,000 times smaller than the diameter of the whole atom. So again, that's tiny. Very tiny little thing sitting in there. Right? And in fact, comparison here to help see that. If an atom size of a football stadium, so if the atom was blown up, or just relative scale here, the size of a football stadium, that nucleus would be the size of a blueberry. One little blueberry stuck right in the middle of it. Alright. It's a strange world when you start looking at the actual atom and the sizes. So all that matter crammed into that blueberry, and all that football, the whole stadium, empty vacuum. Just occasionally an electron whizzing around out there. All right. Um, that's a lot of matter crammed into a very tight space, right? And don't forget that it's the neutron and the proton that have all the mass. Those electrons 2,000 times smaller. Right? So all that mass basically is crammed into that nucleus, which means that nucleus is crazy dense. That is a very dense nucleus. You think of metal, a hunk of lead or something, weighing a lot for the size of it because it's such a dense metal. Well, put that in perspective again. If a paperclip had the same density as a nucleus of an atom, that paperclip would weigh 10 to the 7 tons. What is that? 10 million? 10 million tons? That'd be a heavy paperclip. That's how dense a nucleus is. Alright, so strange world when you get way down that small. Very different. Let's talk about the units here. Atomic mass unit. Again, that's the same as a gram or a pound, or it's the same in the sense that it's a unit of mass. Right? How is it defined? Again, we use it for atoms. We use it down there on that scale. One atomic mass unit is exactly 1/12 the mass of a carbon-12 atom. Remember isotopes? They were different atoms of the same identity, but they had different number of neutrons because they weighed differently. All right? They didn't add charge. No, we're not adding protons or electrons. It was neutrons. You change the number of neutrons, you get different isotopes. Well, carbon-12 is a carbon atom with 6 protons and 6 neutrons. All right. It's probably the most common carbon atom out there. Carbon isotope, I should say. Well, there are 12 things in its nucleus, 12 protons and 12 neutrons. And so, hey, let's take that average mass right there, 1/12 of it, so about the average mass of one of those things in its nucleus, we'll call that 1 AMU, 1 atomic mass unit. So I think that makes sense. We could have chosen another atom, I suppose, another isotope, right? But carbon-12, hey, we're carbon-based life forms, there's a lot of carbon in this world, I guess it's as good as anything. All right, how much does that turn out to be in grams? 1.6605 times 10 to the minus 24. Again, crazy small, hard to even imagine that. All right, but that's how much one proton or one neutron approximately weighs. 1.6605 times 10 to the minus 24. If we go back up to that table, now we can see again when we actually look at that mass, 1.67 times 10 to the minus 24, 1.67. So again, pretty close. They almost weigh the same thing, right on the scale as this. There's a small difference between an AMU, 1/12 of it, and the actual weight of it in an atom. Not going to worry about that. That goes to more nuclear type subjects, and we'll get to that in a later chapter. All right, that's the definition of it. I'll note at this point too that numerically speaking, an AMU is the same thing as a gram per mole, which we also call a Dalton or a DA. Tuck that in the back of your memory. We will get to that in future chapters. They're different units in the sense that one's very small and one's very large, but numerically we can treat them almost the same, and that will make sense later on. We'll come back to it. Okay, so now we have the sense of there's protons and neutrons in the nucleus. Protons are positive, right? Neutrons are neutral. Electrons are whizzing around in this huge space outside of the nucleus. They have almost no mass, but they have a negative charge. Right. So how do we symbolize all this, wrap it up into a neat way that we could write down very quickly? The periodic table of the elements, there's a block for each element out there, and so here's the symbol hydrogen. The atomic mass, so if you add up the weight of all those neutrons and protons and a little extra for those electrons as well, I add it all up, that given in here. So 1.008, that would be in AMUs, atomic mass units. Okay, the name of it, okay, we can put hydrogen on, and the atomic number. Hydrogen turns out to only have one proton in its nucleus. That's why it doesn't weigh very much. About 1 atomic unit. Makes sense, right? So we say, hey, 1 proton, its atomic number is number 1. Right? If we had an element, we had an atom, I should say, with 2 protons, well, we're going to give it an atomic number of 2 then. And that would turn out to be helium, actually. Right? And so here's a couple definitions for you. The atomic number, which we symbolize with a capital Z. Atomic number is simply the number of protons. And as I mentioned before, that's the identity of that atom. If you've got an atom that has 3, for example, we'll go down to a periodic table here. Here we go. That you have 3, that would be lithium, 3 protons. Carbon is number 6 here because it's got 6 protons. Oxygen's 8. Right? So if you look at any of these, very quickly you know how many protons those atoms have. Calcium is number 20. 20 protons in its nucleus. All right. The mass number, well, almost all of the mass is crammed into the nucleus with those protons and neutrons, which weigh about the same, right? And so the mass number is simply the number of protons plus the number of neutrons. How many total do you have? Okay, that's the mass number. It's different from the mass of the atom, but it's going to be pretty close to it. It's a little different because exactly, again, protons, neutrons, they don't weigh exactly the same, and they're not exactly 1 AMU each, but they're pretty darn close, right? And so you get a sense of how much it would actually weigh in AMUs by looking at the mass number, which is you're just counting. Hey, there's 6 protons and there's 8 neutrons. That's a grand total of 14. Mass number is 14. Okay, just add them up. That's simple. All right, and then the number of electrons in a neutral atom, we already talked about that. You'd have to have exactly the same number of electrons in order to balance the number of protons you have, because they do have exactly the same charge, just opposite. One's positive, one's negative. All right. Now, if all that matter is crammed down in that nucleus, very, very dense, there must be some very strong forces holding that together. Why would they cram themselves that tightly in such a small space, right? And so if I'm looking at what can I add or remove from an electron, you know, how can I manipulate it a little bit, it's not going to be with the nucleus. Right? It's going to be with the electrons, which are whizzing around out in that space way outside of the nucleus in that vacuum out there. Now they are fairly easy to add an extra electron, shoot an extra one in there, or maybe reach in and pull an electron out of there. I can manipulate that, but it's pretty hard to reach into the nucleus and change the composition of that. If you do, it takes a lot of energy, and that's nuclear chemistry. Again, that's a totally different branch. We'll have one chapter later on about that. So normal chemistry does not monkey with the nucleus, only with the electrons. That's a very important point. Right. And so, for example here, if I take a carbon atom and I add an electron to it. Now normal carbon atoms have 6 protons and 6 electrons. That's why 0 on the charge, right? It's neutral. But if I add this extra electron to it, it still has 6 protons, not changing that nucleus, right? But now it has 7 electrons, has 1 extra charge on that negative side, right? 1 extra electron. And so now we would say the charge of it is -1. We've just created what's called an ion, a neutral atom. If you give it that extra electron, now it's got a charge. That's an ion. An ion is simply an atom with a charge. Right? Now more specifically, if it's a negative charge like what we just did, it's called an anion. An anion. If I take that same carbon and instead of adding an electron, if I take that carbon and remove an electron, so here I pull it off, what am I left with? It used to have 6 electrons, now it has 5. So if I add that up, 6 positives, 5 negatives, that adds up to a -1 charge, or I'm sorry, a +1 charge. I was thinking of the previous one. All right, and so removing an electron gives it a positive charge. I can't monkey with the protons, only the electrons. I can add or remove them, but by doing so, I can get either a negative or a positive ion. Positive ions are called cations. I want to look at a PhET simulation here that shows atoms, and it's called the atom builder, or build an atom, I guess it's called. Where here the idea of you got a nucleus again, and you got this empty space out here where the electrons go. Okay, and net charge. Let's see, mass number. Okay, we can leave those on. If I add a proton over here, that would be called hydrogen because there's 1 proton, and it's got a charge of +1. The mass is also +1. You know, adding a neutron to that, there we go. Now its mass is up to 2, but its charge is still 1 because, again, neutrons are negative or not. Let's see. Let's go ahead and take that off here. I pulled the wrong one off. Put that proton back on. Okay, there we go. And it is an ion with a +1. If we add an electron out here, all right, now we're back down to a neutral because the positive proton balances the negative neutron. Mass number is not affected by the electrons. Right? The actual mass, yeah, it's bumped up just a hair because the electrons weigh, 2,000 times less, or smaller, I should say, than a proton. but not enough to count really for the mass number. We just count the protons and neutrons. If we add another proton here, now we got two of them. All right. We still have that one electron out here, so it's still got a +1 charge because now we got +2 here and a -1. All we got to do is add another electron out here, and now our charge is back to neutral again. 2 protons, 2 neutrons. Right? That would be helium. Right? Now you see on my simulation it's shaking. It says, hey, unstable, unstable. What's the problem? Well, you're trying to cram 2 protons down here into the nucleus. Protons, being both positive, would want to repel each other, actually. The neutrons down here, if I add a neutron there, oh, now it's stable. You see, the neutrons kind of act like the glue, if you will, to keep all those protons from just poof, blowing apart from each other. Because again, protons being all positive, they're going to repel. Kind of like trying to cram the same 2 magnets together where you put the north and the north, and yeah, it's hard to do if it's a strong magnet. Same idea here. We can add a little more glue, a little more neutron. It's still stable. That's increasing now up to 4 for the mass number because I've got 4 things in the nucleus. I can't go too far though. You see, if I try to do too much, then it becomes unstable as well. You can you need the right ratio of protons to neutrons. All right, let's go a little more. Here's another proton here. Now we got 3 of them. We need some glue. Need some neutrons in there. All right, now we got a stable lithium. It's an ion because, well, there's 3 protons and only 2 electrons. Let's make it an actual neutral electron or atom. There we go. 3 electrons, 3 protons. Now it's neutral. All right, so you get the idea. Build an atom is kind of fun to play with, and you can get a sense of where those particles are in an atom. All right, now symbol-wise, to show these different elements and the different atoms and the different sizes, we can use 1 or 2 letter symbols, such as carbon, capital C, or magnesium, capital M, lowercase g, Mg. Rule, if it's only 1 letter, it gets capitalized. If it's 2 letters, the first letter is capitalized, the rest, the second letter, is not. Okay? And so pretty simple. We go through and take a look at some of these common ones. I've got this in yellow, and I say memorize. The ones in yellow are the more common atoms out here. These are the ones that you need to memorize. Okay? By memorize, I mean the name and the symbol. Not the mass, not the atomic number, just the name and the symbol. All right, so hydrogen, capital H. Helium, He. Lithium, Li. Beryllium, Be. Oh, and do know how to spell it too, beryllium. Don't spell it incorrectly. Boron, carbon, nitrogen, oxygen, fluorine, neon, all the way across. So all these yellow ones, get those down. Here's tungsten. That's a little different, strange one. It's a W. Uranium is the only one down here on the bottom. That's a U. Okay. Why do some of these have strange letters? I mean, for example, sodium. All right, it's part of salt, sodium chloride. That's table salt. Na. Where in the world does Na come from? Now, I guess I understand sodium. You might think S, but you know, over here sulfur is S, so I can't use that. But still, Na. Why choose that? Well, actually, it goes back to the old Latin name. Some of these things have been known for quite a while, and the old Latin name for sodium, if you look over here, is natrium. Is that even on this list? Am I missing it? There it is. I just missed it. There we go. Sodium. The old Latin name was natrium, and so Na all of a sudden makes sense. Okay. Other odd ones are in this block here. I put this little table up on Moodle, and there's a similar table in your textbook. Okay. Antimony is Sb because it used to be stibdom. Copper, Cu because of cuprum. Gold was aurum, iron was ferrum, so etc., etc. So yeah, some of them are a little odd. You got to get them memorized, but the odd ones make sense when you realize their origins. Okay, remember the term isotopes? Isotopes were atoms with the same identity, but yet they weigh differently. And we talked about, well, they weigh differently because they have a different number of neutrons, different number of glue particles, if you will. And as long as you're within this narrow range of what's stable, well, we expect them to exist. So different number of neutrons. They're all carbon, for example, here. It's just this carbon one has 6 protons and 6 neutrons. This carbon 13 must have 7 neutrons. 6 protons. This one must have 8 neutrons, 6 protons still. They all have 6 protons, otherwise they would not be carbon, but different number of neutrons. And so we put this little number on the top left of the symbol to show what its total mass number is, the total number of protons plus neutrons. How much does this thing weigh just as far as counting protons and neutrons? Carbon 12, carbon 13, carbon 14 as an example. All right, so sometimes, as they showed here in your textbook, we can put these numbers around our symbols to further clarify things. The top number, the mass number, protons and neutrons. That'll tell us which isotope we have, right? The bottom, the atomic number, the number of protons only, right? That's the identity, the atomic number. It's number 2, that's what makes it a helium. So this is actually a little redundant if you think about it. I could say, hey, I've got an atom with 2 protons, or I could say, hey, I've got a helium atom. Either way, you know exactly what I've got. I've got this atom, 2 protons, it's called helium. I mean, that's what the one means the other. All right, so that's redundant, therefore it's often omitted. All right, but that top number, because there are different isotopes that exist, that tells us between those guys. And if this thing has a charge, well, we can put that up here. I've got 2 positives. I've got 3 negatives, whatever. If I have 0 charge, well, we don't have to put a 0 up there. Okay. So, for example, here's magnesium 2412 with a 2 plus. So this is a magnesium ion. It's lost 2 electrons. That's why it's got a +2 charge there. It's got a total mass, that is to say protons plus neutrons, of 24. And it's got, of course, 12 protons. Why does it have 12 protons? Because, oops, and I just hit the wrong thing. Sorry about that. This is what I meant to hit. What are we talking about? Magnesium. Magnesium normally has 12 here on our table. And so the fact that it's got 24 total mass must mean there's also 12 neutrons. It doesn't always turn out to be the same. So far, carbon 6 and 6 or 6 and 7, it's going to be close, all right, but it's not have to be the same. Here it's 12 and 12 for this magnesium. Actually, the larger, the bigger atoms you get, the more neutrons you'll find are needed, the more glue, if you will, to keep that thing stable. Okay, so here's some examples, if you will. Actually, before I go to that, let's go back to the PhET simulation here, because they have a slightly different mode where it shows a symbol. Right? Same idea here. Here's a symbol, hydrogen. Right? Mass number of 2. So a total of 2 protons and neutrons. There they are. One's a proton, one's a neutron. Of course, since it's hydrogen, I know there's only 1 proton, and there it is. It's a +1 charge, so I must have lost an electron. Well, hydrogen only had 1 to begin with, and so there's no electrons out here. Let's go ahead and add an electron to this guy. There we go. Now we have no charge at all. And again, you wouldn't normally write this is 0. Right? If we add some more neutrons to it, oh, now it's going to be heavier. Mass number is 3. Still 1 for the proton and 0 for the charge because that 1 proton and that 1 electron balance each other. Let's go to a different identity. Let's throw some more protons on here. Let's go bigger this time. Why not? Let's get quite up there. Oops, let's show if it's stable or not. Yeah, not very stable because I didn't put any glue in there. We're going to have to add quite a bit of glue, I think, probably. Ah, there we go. So boron here. Boron has 5 protons. Right? Of course, I only have 1 electron, so it would have a +4 charge. Let's go ahead and add some more electrons to this and make it a neutral atom. There we go. 5 electrons, 5 protons. Now it's neutral over here. Right. 10 for the mass number, so I have 10 protons and 10 neutrons. Yeah, that's stable. So here's one of the stable isotopes of boron. All right, call it boron 10. Let's try adding another neutron to it. There we go. It's still stable. This would be boron 11. Different isotope. Go up here. Boron 12. Too many neutrons. Not stable anymore. All right, so you get the idea. I wonder if it lets me go up here. Here's carbon. All right, let's actually remove one of these neutrons. All right, unstable. I need at least exactly 6. So here's carbon 12, stable isotope of carbon. Of course, it's an ion because I didn't match it. There we go. Now it's got 6 electrons, 6 protons. It's carbon 12. Add another neutron. Here's carbon 13, stable. Add another one. Carbon 14, that's unstable now. Right? So if I had a carbon 14, in other words, it's not going to stick around for very long. It's going to do a nuclear decay, and again, that's a subject for a later chapter. But the 12 and the 13 isotopes are plenty stable, and I expect to find them out in nature. Okay, here's a table from the textbook here that shows, oops, I'm trying to scroll, sorry about that, that shows some common isotopes of carbon nitrogen, and oxygen to give you a sense of it. So here's the carbon-12. Right, 6 protons, neutrons, 6 electrons. Its mass is 12. All right, 98.89% of the carbon isotopes out there are carbon-12. Right, it's a stable isotope. Most of them are that. Carbon-13 we saw on the PhET simulation was also stable, but it's only 1.11% actually of what's out there. Carbon-14 was unstable. We know it can exist, but it doesn't stick around for very long. They just say, it's just a very small trace amount of it. So basically, it's all the carbon that you and I are made of, all the carbon that's out there in the world, carbon-12 and carbon-13. Which is why, if you add up their percentages, this is going to add up to 100%. Okay. Nitrogen, you got nitrogen-14 and nitrogen-15. Those are the two stable ones. And it looks like most of it's actually nitrogen-14. Oxygen, 16, 17, 18, there's the relative abundances, the percents of those isotopes of all the oxygens. There is usually one isotope that is by far the dominant, by far most are, and then you got smaller percents of other ones like that. Alright, last thing to talk about in this section is the average atomic mass. Periodic table. So let's pull that up again, periodic table. I wonder if I can zoom in on this a little bit. Well, it's okay, you can see it. If I look at that, there's these numbers down here at the bottom. Iron 55.847 or carbon 12.011115. Where do these numbers come from? I mean, for example, let's look at the carbon one. 12.011115. This is the mass in AMUs of a carbon atom. Right? 12.01115. Well, if I go back and look at that table of isotopes that we were just looking at, carbon has these different masses: 12.000, 13 for that isotope, 14.032 for that isotope. And yet on the periodic table, I don't see exactly 12 or exactly 13.0334 or exactly 14, right? On the periodic table, I see 12.01115. What gives, right? Where does that number come from? Well, since all of these isotopes of carbon exist and are out there in nature, that number that's reported on the periodic table is simply an average of them. It's an average. It's not a simple average, though, so you got to be careful there. All right? Let me show you what I mean. If you look at this table here, we've got the fact that, you know what, I'm going to just slide this over here and use the space and write directly on here. I think this will be the easiest way to do it. Okay. If you look at the 3 carbon atoms that are out there, we've got carbon 12, 13, and 14, and here's their masses and their relative abundances. You see, if I was to say, okay, well, let's average those together, I know how to take an average. The mass of the first one is 12.000. I would add to that the second one, which is 13.0034. And then add to that the next one, which is 14.0032. Add those guys together. Let's go over to my calculator here, and let's punch that in. I've got 12.000 plus 13.0034 plus last one 14.0032. So that's 39.0066. Divide that by 3, and I would get 13.0022. So that average is 13.0022 AMUs. Clearly that's not what's on the table, right? It was 12.011. Where does it come from? Again, it's not a simple average. That's the problem with that calculation. So let me just erase that. Let's get rid of that. What they do is what's called a weighted average. You see, if I'm going to truly do an average of these different isotopes of carbon, well, this one, the very first one, carbon-12, is 98.89% of them out there is that. Which means if I look at the average mass of the carbons out there, it should be pretty close to 98.89 since most of them are that. Okay? Just a little bit, 1.1% are this heavier 13, and then this one's a trace. I'm not even going to include it, so small, 14. Okay? Barely is going to affect it at all. Alright, here's how you would do a weighted average then to account for that. This first one, which weighs 12.000, I simply multiply it by its relative abundance, which is 98.89%, or in fraction or decimal point form, 0.9889. Right? Now I'm going to add to that the second one, which weighs 13.0034, but it is only 1.11%, or in decimal 0.0111. Right? All right, let's add those things together. Get my calculator here. 12.008, no, 000, excuse me, times 0.9889. Plus the second one, 13.0034 times its abundance, 0.0111, equals, what do you know? Look at that. The answer over here, 12.0111. And that's exactly, sorry, my pen isn't working, 12.011. That's exactly what we saw on the periodic table. Again, let's pull that up. Carbon, 12.01115. These numbers are the average masses of the isotopes, but they're not simple averages, they're weighted averages. You simply take the weight of the isotope times its abundance. Weight of the isotope times its abundance. Add them all up and you'll get the number that's on the periodic table. You'll get the weighted average. Okay, that concludes this section. Actually, it does conclude the section, but let me point out one last thing. Here's the actual equation to calculate the average mass. Okay, mass with a bar over the top, that just means average. So okay, average mass here. At least that's one way to indicate average. The fraction, that is to say the relative abundance, the fraction of the first, second, third, I is just the counter here. So the first one, the fraction of the ith times its mass. This capital sigma just means sum. Add them all up. All right. So the average mass is just the sum of the fraction times the mass of each individual isotope. Example 2.4 from the text. I did an example for you, but let's take a quick look at that here. Scroll up to 2.4. We already talked about all this stuff, didn't we? Okay, I think we're getting close now. Isotopes. There's that complete chart for you. Hey, okay, here we go. Example 2.4. A meteorite in Indiana contained traces of the noble gas neon, picked up from solar wind, blah, 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 blah. Okay, all right, analysis of the sample showed it had 91.84% of neon-20. There's its mass. 0.47% neon-21, and 7.69% of neon-22. And there's its masses. What's the average? So what are we going to do? We're going to take one by one, 91% times its mass of 19.9924, 0.47% times its mass, 7.69% times its mass, and add them all together. Now don't forget to convert to fractions, those decimals, I'm saying those percents, excuse me, convert them to decimals. All right, so here we got it, 0.9184 times the mass, exactly what I said. We're just multiplying together, adding it, they get 20.015. So the average mass of neon would be 20.15 AMUs. Okay, now that finally actually does conclude this section.